So we looked at the idea that changing the area, the distance between the plates, or the dielectric that's in between the plates can change the capacitance. That's not always going to be possible, considering if you go buy capacitors from an electronics store, you can only buy them in certain amounts, say 1000 microfarads, 470 microfarads, 220 microfarads, and so on and so forth. So you can't necessarily buy one that's, say, 550 microfarads. One of the ways, though, that you can introduce that sort of capacitance in a circuit is to combine capacitors. So in the same way that you can combine resistors, we can do the same with capacitors. So to look at how that happens, we're just going to deal with the two situations that we need to consider. The first is if you've got capacitors in parallel. So that would be a situation where we've got, say, a parallel branch with one capacitor at the top and another capacitor at the bottom, and current flowing through. So let's call this one at the top C1 and the one at the bottom C2. Now when they are charged, we're going to have a common voltage or a common potential difference between the two. We'll call that V. So whether it's going through C1 or C2, because they're in parallel, the potential difference across them will be the same. That means that the charge that builds up on each one, Q1 and Q2, will be different. So we then have that for C1, going back to the formula that we saw previously, Q1 on V is what we could use to figure out what the charge is on that particular capacitor C1, and similarly for C2 it would then be Q2 on V. Now if we were to consider what the total equivalent resistance is, we'd basically be taking that situation and replacing the two capacitors with one single capacitor. The quantity that's going to be the same here is the potential difference across it. The charge that we would consider, so we'll call that QT, and then we'll just call the capacitance C. Now if we think about what's happening in this situation, total charge stored then will be given by the sum of the two charges Q1. So that's going to be Q is equal to Q1 plus Q2. So it makes sense if we replace by a single capacitor the amount of charge that we built up on these two capacitors individually would have to add together. Now if we take that expression for C1 and rearrange it, we get that Q1 is equal to C1 V, and likewise Q2 is equal to C2 multiplied by V. Now if we think about the total charge that would be stored on the capacitor QT, and then compare it to the total equivalent capacitance C and the potential difference, we would have that that's actually equal to C multiplied by V, and then we can substitute in for Q1 and Q2, and we'd have that is C1V plus C2V. Now you can see that we've got V in every single term, so we can cancel those V's, and we're left then with the equivalent capacitance C simply being the sum of the two individual capacitances. So that's for capacitors in parallel. Note that it's sort of the reverse of what it is for resistors. So resistors in series, you just add the resistances. Capacitors in parallel is where you add the capacitances. So it's sort of a little bit of a back to front compared to what happens with resistors. Moving on to series capacitances, you probably can already figure out here that it's going to be similar to resistors in parallel. In this situation, I'll go through and explain how it arrives, or how that the equation that we end up with, how it comes about. Again, we'll call these C1 and C2, and the potential difference across here now is not going to be the same. So it's going to be potential difference V1 and potential difference V2. I'm going to make a note here first before we talk about the charge. In charging them up, the same current is going to flow, or the same current charges both capacitors. Now you might look at that and say, well, hang on a second, how do we get any charge occurring through the middle? What ends up happening there is that we have, say, if the current's flowing from right to left, so electrons are being pulled off the this plate on the left hand side here, then that plate becomes slightly more positive. So this one becomes slightly more positive, and this plate over here becomes slightly more negative. That means that all the electrons in this middle section will therefore be repelled by this negative and attracted to this positive plate, so this plate becomes negative and this plate becomes positive in equal measure to the charge that's building up on the negative plate and the charge that's building up on the positive plate of C1. So we still do get that separation of charge through that middle section as well. So as the same current charges both capacitors, they will both store the same amount of charge. So that means the value of Q will be the same for both of them. So this one's going to have charge Q, and likewise C1 will have charge Q. So we saw before C1 is going to now be Q on V1, and C2 is now going to be Q on V2. And if we consider now instead, we're going to look at the fact, sorry, let me go a step further before I say too much more. If we now look at basically looking at Kirchhoff's laws, and in particular the loop law, the total voltage across the two capacitors, so that's if we're looking at this total voltage across here, that potential difference V is going to be equal to V1 plus V2. So the sum of the from beginning to end is going to be equal to the sum of, the total from beginning to end is going to be equal to the sum of the two. That means from the first equation, we can write then that V1 is equal to Q on C1, and V2 is equal to Q on C2. Now, if we're considering similar as to what we did before, if we take that whole situation and replace it with a single capacitor, so this now has a capacitance C, potential difference across it is going to be V, given that we're replacing these two with a single capacitor, and the charge there will still be Q. So that then means that this potential difference V, similar to what we did with rearranging the two above, we can express that as being Q on the total capacitance C, and as we saw, V1 is equal to Q on C1, and V2 is equal to Q on C2. Common term of Q through all of those, so if we cancel that out, we end up with 1 on C is equal to 1 on C1 plus 1 on C2. And again, an important equation there that is in the data booklet. So you can see with both of those we've got the addition to figure out the total in series or the total in parallel. If you had more than two capacitors, then you can literally just add, so let's say you had 3 in series, you just add another term there, 1 on plus 1 on C3, and so on and so forth. Likewise with in parallel, if you had a third in parallel, just add another term on the end there. And as a result, that then means that with a stock standard set of capacitances, you can then start to add them together in different ways, different, say, two 100 microfarad capacitors. If you put them in parallel, will give you a total capacitance of 200 microfarads. If you put them in series, then it'll give you a total capacitance of 50 microfarads. So you can use those combinations to come up with just about any range of capacitances you might need.